Hello and welcome to 90 East. In this video we'll be looking at how to calculate the relative atomic mass for a sample and comparing that to the standard atomic weight for the chemical element. You'll remember from our previous video that the relative atomic mass is the average mass of an atom within a sample, irrespective of where that sample comes from. So it could be from our planet, or it could be from outer space, say for instance from another planet like Uranus. The standard atomic weight, on the other hand, is the average mass of an atom that's from a normal sample. And by normal, we just mean something that you'd probably find in your science lab or in industry, something that hasn't been significantly changed. Now, in this video, we're going to work through 3 different examples, but you'll find in the description box below a worksheet of examples or exercises that you can work through in your own time to consolidate your understanding. So without further ado, let's get started. So in our first example, it's quite similar to the one that we used in our last video, but with larger numbers. So we've got a given sample of 20,000 chlorine atoms, and we've got 2 isotopes, chlorine-35 and chlorine-37. If you remember from our last video, there's 3 things that we need to know about a sample to make sure that we can work out the relative atomic weight: the number of isotopes, their relative abundance, and the atomic mass of each isotope. So let's put in the numbers here. We've got the 2 chlorine atoms, their relative abundance, so the number of atoms of each, and their atomic mass. You'll probably also remember from our previous video this equation here, where N1 is the number of atoms of isotope 1, or isotope 1's relative abundance, and Ma1 is that isotope's atomic mass. And then the number of atoms is the number of total atoms, so in this sample 20,000 chlorine atoms. To make the most of this video, we suggest that you pause and actually put these numbers into the equation and calculate the relative atomic mass, and then compare it to what we've calculated. So the numbers that we've put into this equation look like this. If you calculate that a little bit further along, it looks like this. And the final numbers will look something like this, where the relative atomic mass is 35.459, or if we reduce it down to 4 significant figures, 35.46. Now let's compare that relative atomic mass to the standard atomic weight of chlorine, and that is 35.45. The numbers are almost identical, which means that this sample here is pretty much a sample of normal chlorine atoms. Okay, now let's look at our second example and how we'd calculate the relative atomic mass when the abundance is expressed not as number of atoms but as a percentage in the sample. In this one, we're looking at bromine atoms, and we've got 20% of the atoms are bromine-81 and 80% are bromine-79. And this is the atomic mass or isotope mass of each atom. So now we need to calculate the relative atomic mass. To ensure that we can do that, we'll just make sure we've got all the information. So the number of isotopes, yes, their relative abundance, yes, and the atomic mass. Now we just need to look at the formula, and it's a slightly different formula to the one that we used in the last example. Rather than N1, we look at F1, and F1 is a fraction of an isotope within a sample. If you'd like to work through the exercise by yourself first, then pause the video here. Otherwise, let's get started. So let's plug our numbers in, and it looks like this, where 1/5 of the sample is made up of bromine-81, and 4/5 is made up of bromine-79. If we work out the multiplication here, these are the numbers that you should come up with. And then the final relative atomic mass is 79.32, or if we reduce it down to 2 significant figures, 79. Let's compare that now to the standard atomic weight of bromine, and that is 79.9. While it looks similar to the value that we've come up with, it is slightly different, and that means that this sample here is not a normal sample. Okay, now let's move on to our last example, and in this example we're going to be looking at a sample that has got many different isotopes within it. Titanium-46, 47, 48, 49, and 50. We've got their relative abundance up here, which we can put down there just to keep things nice and simple, and the atomic masses for each isotope. Because the abundances are given here in a percentage, we'll use the same equation that we used in the last example, but because we've got 5 different isotopes here, we need to extend this equation out to include 5 different isotopes. If you'd like to work through the exercise by yourself, pause here. Otherwise, we'll plug in the numbers right now. So if you put the numbers carefully in, this is what you should come up with. Do the multiplications, and this is what you should come up with. Do the additions, and you can work out that the relative atomic mass, when reduced down to two significant figures, is 48. Now the next question is this a normal sample? We just need to look at the standard atomic weight to decide that, and that is 47.86. Compare the two numbers, then yes, this is a normal sample. So, to review, the relative atomic mass of a sample is basically the average atomic mass in that sample, whereas the standard atomic weight is the average atomic mass in a normal sample. And we've worked through 3 different examples in this video. As we've already mentioned, there is a worksheet down below that you can download and work through in your own time. And if you've got any questions, please directly send us a message through YouTube or email 90easttv@gmail.com. Thanks everyone.